two aren't here. And I want to pick back up with question 5 that we ended on Tuesday, because when I went back and was looking at the actual review sheet in D2L, after you've conducted the two mean hypothesis test on this particular scenario for scenario 5, it asks you to conduct the post hoc test, Cohen's d. And we did not look at how to, or review how to calculate Cohen's d. So if you'll remember, Cohen's d is a post hoc test. So you would do this after the initial hypothesis test. Okay. And we're going to do, it's called a post hoc test. And we're going to do Cohen's d. Now you may need to refer back to one of the PowerPoints and one of the slides. And so I want to point out which one. It is in, let me make sure I tell you the right module. So let me go back over here to the course. It is in module 3, and we want the two mean t-test hypothesis testing. Okay, so you may need to look at the PowerPoint. And it's under module 3, two mean t hypothesis testing. Specifically in that PowerPoint, you want to look at slide 6. Really for two reasons. One is on slide 6, it gives you the formula for calculating Cohen's d, but it also gives you the table that we use for determining the size of the effect, because that's the follow-up question, excuse me, at D2L. So the formula is you take the difference divided by the pooled standard deviation. So I'm initially going to perform that calculation. So Cohen's d is the difference divided by the pooled standard deviation. Now those two values come from Minitab, and you get those results, and I went ahead and worked through it this morning so we would have it up and running. But you do stat, basic statistics, to sample t, and we have summarized data, and I re-entered the data that we had entered on Tuesday, and you get your results. For Cohen's d, we need the information under the header estimation for difference, and in that result area it gives you the difference which we need for calculating Cohen's d. So the difference will be negative 1.90 divided by 9.88, which is the pooled standard deviation. And then I'm going to use my calculator. So I have negative 1.90 divided by 9.88, which gives me approximately negative 0.1923. And so then I have to decide what the effect size is. And again, we're going to use this chart or table on slide 6. And so I am actually below or a little bit above negative 0.2. So it's going to be a small effect. Okay, so this would be a small effect. So I realized I had missed that on Tuesday when I was going back to look at the information about the final exam. So I wanted to make sure to cover that particular item this morning. Good morning, Jeannie.
Good morning. Sorry I'm late and I'm going to have to jump off early. I'm in between meetings.
It's okay. I completely zoned out this morning and missed a meeting, so I was telling
I could completely zone out and miss a meeting.
I didn't mean to. But I was telling Naomi on question 5, where we ended on Tuesday, when I went back and was looking through the review and the test itself, you need to calculate Cohen's D for that 2 mean t-test. And so I've worked through that. I've recorded it so you can go back and watch that, but you will need to refer to the PowerPoint for under module 3, the 2 mean t hypothesis testing, slide 6, because one, it gives you the formula for Cohen's D to calculate it, but it also gives you the table that you need to determine whether it's small, medium, or large. So I went through that. So let's move on to question 6, if you ladies are okay, because I want to try to get through the rest of these, either here virtually, or I'll finish out the recording so you'll have them to refer to. So scenario 6 says, for Americans using library services, the American Library Association claims that at most 67% of patrons borrow books. The library director in a town feels this is not true. So she asked a local college statistics class to conduct a survey. The class randomly selected 100 patrons and found that 83 borrowed books. Did the class demonstrate that the percentage was higher than 67%? Use alpha equals 0.01 level of significance. So again, we're back to this idea of hypothesis testing. Again, we have to identify which test we have. One of the things that almost immediately jumps out at me in this particular problem is that I have a percentage, which is a, synonym for a proportion. And as I read through it, it really is only talking about one proportion, and that is the proportion of people or portion of Americans who borrow books from the library. And so that leads me to the fact that this is a 1 proportion Z test. So we begin, as we always do with any hypothesis test, and we state the hypotheses. So you have your null and the alternative. I would encourage you on this particular problem to be careful, because in the claim made by the Library Association, it says at most 67%. But if you go to the end of the problem where the question is, it said, did the class demonstrate that the percentage was higher than 67%? So really your hypothesis in this problem is this statement here. This was the hypothesis of the class, that the percentage of patrons who borrow books is higher than 67%. So higher to me would imply greater than, which means that particular statement is the alternative. So we're saying that our proportion is higher than 67%. Remember, we do write the percentage as a decimal, and this is the one that's given. The null, remember, always contains equal and would be the exact opposite. So it would be less than or equal to the 67%. In step 2, we identify the players, and you may have forgotten what the players are for proportion test. You need P, which is your population proportion, and that's going to come from the hypothesis. You have X, which is the number of events. That's what they call it in Minitab. It's basically how many times do you get what you want. N is called the number of trials. That's like your sample size. How many times did you conduct the experiment? How many people did you survey? And then, of course, as always, we need alpha, which is our level of significance. So if I go back and look at the story, I get population proportion from the hypothesis. So that's the 0.67. It said the class surveyed 100 patrons and 83 of them, I believe, let me double check myself. 83 borrowed books, and it tells us to use a 0.01 level of significance, which means our confidence level would be 99%. So then we move on to step 3. Step 3 is to calculate the test statistic, and that'll be a Z, and its p-value. So I'm going out to Minitab. Stat, basic statistics, 1 proportion. I have summarized data. The number of events was 83. There were 100 patrons surveyed. We are performing a hypothesis test. My hypothesized proportion is 67%. My confidence level is 99. We are saying that it is greater than, and we do a normal approximation. Then I click OK. I click OK. And the results appear. Again, we look for the header labeled test. And I'm going to copy that over here to my paper. Okay, so from Minitab, we can find our Z and our P, which we record. The Z is 3.40, and the corresponding p-value is 0.000. Step 4 is to make a decision. We make a decision by comparing the p-value to the level of significance. P-value comes from Minitab, and in this case is 0.000. The level of significance was given in the problem as 0.01. Compare them digit for digit. 0 to 0, 0 to 1. 0 is less than 1. So P is less than the level of significance, less than or equal to. If P is less than or equal to the level of significance, we reject the null. So in this problem, if we reject the null, that means the null is false and the alternative is true. So based on the evidence that we have proven the percentage is higher than 67%. And so in my last step, we're going to write the conclusion. Remember that your conclusion always includes your level of significance. So at the 0.01 level of significance, the proportion of library patrons who borrow books is higher than 67%. Honestly, the process is not changing, guys. It's a matter of which hypothesis test you need to conduct. Scenario 7 reads, the National Health and Nutrition Examination Survey is studying childhood obesity. The researchers weighed a sample of 546 boys aged 6 to 11 and found that 87 boys were overweight, and the researchers weighed a sample of 508 girls aged 6 to 11 and found that 74 were overweight. Can we conclude the proportion of boys who are overweight differs from the proportion of girls who are overweight? Boys is proportion 1, girls is proportion 2. So again, thinking about these words in this statement, at the end of the problem, it says boys is proportion 1, boys is proportion 2. So again, that kind of tells you that you have proportions and that you have 2 of them, because they're telling you this is 1, this is 2. So again, that should hopefully lead you to the 2 proportion z-test. So we begin, as we always do, by stating the hypotheses. So we have our null and we have our alternative. And if I look in this problem towards the end, we find our hypothesis. Can we conclude the proportion of boys who are overweight differs from the proportion of girls who are overweight? So we have the word differs. we have the word differs. Differs means they're not the same, which mathematically would be not equals. So that statement would be the alternative. Now, I prefer to say the proportion of boys does not equal the proportion of girls. You could say proportion 1 does not equal proportion 2. But then you have to remember that 1 is boys and 2 is girls. So you can write it either way. The proportion of boys equals proportion of girls would be the null hypothesis, okay? Because remember, they have to be opposites of each other. Okay, then you've got number 2 is to identify the players. And in this case, you're going to have information about the boys, which is proportion 1, and the girls, which is proportion 2. You need basically the same 3 pieces of information that you needed for the oh my goodness, for proportion 1, because you need the number of trials, how many did you have in each group, and you need X, how many had that particular issue. Okay, so 546 boys were surveyed and 87 were overweight. We surveyed 508 girls and 74 of them were overweight. And we also need our level of significance, or alpha, and it was given as 0.05. If the significance level is 0.05, our confidence level is 95%. Then question 3, you calculate the test statistic, which again in this case would be a Z, even though it's 2 proportion, and its p-value. And we're going to do that in Minitab. Stat, basic statistics, 2 proportions. Stat, basic statistics, 2 proportions. Again, we have summarized data for the sample 1, which was the boys. There were 87 out of 546 that were overweight. Sample 2 is the girls. There were 74 out of 508 that were overweight. Under options, we are using 95%. The hypothesized difference is 0, so they're not equal, and I believe we were using the pooled estimate. I can't remember. Okay, so again, we get the results and we want to look at the test results. Whoops. Okay, One thing to think about with our test results, remember, you want to read the values related to the normal approximation. The normal approximation. So in this case, Z is 0.62. That's our test statistic. And the p-value is 0.538. I also noticed on the document that we were looking at the other day, on which test should I use, I realized that I had omitted the two mean proportion test. So I'm going to go back and add that to the document, and then I'll update it in the announcements for you. Okay, so this particular one was not listed there for whatever reason. I just missed it. So then step 4, we make a decision. We compare the p-value from Minitab to the level of significance. So I have 0.538, that's my p-value, compared to my level of significance, which is 0.05. Again, you compare those digit for digit. So 5 compared to 0, 5 is greater than 0, P is greater than the level of significance, so we fail to reject the null. Again, thinking about what that means in this context, if we fail to reject the null, that means the null is true and the alternative is false. So based on the evidence that we have, we've shown that the proportion of boys who are overweight does not differ. It's actually the same as the proportion of girls. So step 5 is to write the conclusion. So we would say at the 0.05 level of significance, the proportion of boys who are overweight do not differ from the proportion of girls who are overweight. And there you go. Questions? Scenario 8 says, in a recent poll, 668 American adults were asked their opinion on whether the government should prohibit smoking in public areas. Additionally, each was asked how many people lived in his or her household. And the table below shows the results. So a couple of things to notice. One is you are given a two-way table. Furthermore, if you look, the responses to whether the government should prohibit smoking or not are words, which is qualitative data. The only test that we talked about that uses qualitative data is chi-square. But I need to decide which chi-square test it is. So if I use my document, which test or which distribution should I use? And I look at chi-square. If I remember correctly, we did a goodness of fit earlier, and typically the question with goodness of fit is, does it fit or follow a known distribution? Well, that wasn't the question here. The question here was, it didn't really state a question, I don't think, table below, but it looks like they're trying to see if there's some sort of relationship between the size of the household and whether that they agree or disagree about the smoking. So if I go back and look at this document, notice that we have basically two survey questions, because they ask them question one was their opinion about smoking, question two would have been the size of their household. And so that makes me think of the test of independence. If I keep reading, notice that test of homogeneity says single survey question asked to two different populations, but we had two questions. So again, this makes me think that this is going to be a chi-square test of independence. So question one, as always, is to state the hypotheses. Now, the hypotheses for a chi-square test of independence are pretty much stated the same way. What changes is your variables. So in this case, we would say smoking, opinion, and household size are independent. Okay, and again, that implies in this context that they're equal. Your alternative would be the smoking opinion and household size are dependent. Okay, so for chi-square test of independence, your null will always indicate the variables are independent, and the alternative will indicate that they are dependent. Step two is to identify the players, and our players really have already kind of been identified for us because it's this table. But we also need our level of significance, and it tells us to use alpha equals 0.05, which then means my confidence level is 95%. So then I'm ready to do step three, which is to calculate the test statistic, but we have to basically recreate this table in Minitab, which is a little awkward to do. So I'm going to go over there and do that, but let me write down step three. Step three is to calculate the test statistic which is chi-square and its p-value. So I'm going over to Minitab, And again, I have to try to basically type in this table. So the way we do it is in column 1, we're going to put the options for the opinion about whether the government should do something about smoking in public areas. Then in the columns 2, 3, 4, and 5, we're going to have our household size. So we would have one household where there's one person in the household. We'd have one person, 2 people, 3 people, 4 people, 5 people. Okay, so the other columns, the first column becomes your words. So we had agree, no opinion, and disagree. And then we're going to fill in the blanks. So we had 73, 31, 42, 52, 71. You want to be careful, double check, make sure you get the numbers in right. I don't need a comma. Oh man. Oh, I'm sorry, guys. I made a mistake. Okay, so that's 3, 48, 29, 38. 4 people is 37. Okay, again, it took me a minute to get it in there. It's a little awkward trying to get that table in there. Okay, be careful. Make sure you double check your numbers. So I've got my two-way contingency table entered. Here's how you do test of independence. Stat, tables, chi-square, test for association. I have summarized data in a two-way table. The columns represent the household size. They're in column 2, 3, 4, 5, and 6. The rows represent the smoking opinion. The columns again were the household size. We do statistics. I don't need to change anything there. And I click OK. And again, remember, we get lots and lots and lots of information. But what we're looking for, again, is our chi-square test. And again, remember that we are using the Pearson, which would be our top row. And so for this problem, my chi-square test statistic is 5.422, and my p-value is 0.491. Then, as always, the next step is to make a decision. We're going to compare the p-value to the level of significance, which is alpha. So we have 0.491 compared to 0.05. When I make that comparison, 4 compared to 0. 4 is greater than 0. P-value is greater than alpha. When P is greater than alpha, we fail to reject the null. So in this context, if we fail to reject the null, okay, that means the null is true and the alternative is false, and the two variables are independent. Household size does not affect someone's opinion about smoking in public places. So step 5 is to write the conclusion. So we would say at the 0.05 level of significance, public smoking opinion and household size are independent of each other. Questions? Scenario 9 says, do male college students and women college students eat 3 meals a day? The data below is collected from a random sample of college students at a historically black college and university. Use a 0.05 level of significance. And so again, in this scenario, we're given a two-way table. But I also again notice that the response for at least one of the variables was words or qualitative data. So again, that makes me think of chi-square. Looking at my which test should I use document, we just did test of independence. We've already done goodness of fit. It's likely homogeneity, but look at the conditions. A single qualitative survey question asked to 2 different populations. So we were asking, do you eat 3 meals a day? And we're looking at males and females. So I've got 2 groups, 1 question. So this one is test of homogeneity. So we do begin, as always, by stating the hypotheses. Okay, so we would have, let's see, we're saying that they're the same. And I'm trying to remember kind of how they word that. We could say male students and college and women college students eat 3 meals a day, since we're specifically focusing on 3 meals. Let's look at, just so I don't confuse you, let's go out and look. I want to make sure we use similar terminology to avoid confusion. And let me go out to this review and just double check. Don't want to give you any confusion. Okay, I know it's near the bottom. Let's start right here. Okay, the way they word it is they say the distributions for 3 meals a day are the same for males and females. Okay, so I mean, there's lots of ways we could say it. Again, what you got to say is that they're the same or equal for the null, and it would be not equal for the alternative. So we're saying the distribution of 3 meals per day is the same for males and females. Again, the null implying that it's equal. The alternative would be the distribution of 3 meals per day is not the same for males and females. Okay. Our step 2 is to identify the players. And again, in this case, our players are the table. Along with our level of significance, which is 0.05. So the confidence level is 95%. And again, we've got to go out and try to put that table into Minitab. So I'm going back over to Minitab, and I'm going to get a clean sheet so I don't get messed up. Okay, so again, the first column is going to be, in this case, going to be the gender, whether they're male or female. And then we have usually eat 3 meals per day, and we have rarely. Okay, then we fill in the numbers. Whoops, Miss Ralston's in the wrong blank. She's having trouble this morning. Okay, so we get the data entered. Again, it's a contingency table. It's the same commands that we used for test of independence. The difference is how the data is interpreted. I did look that up and research why but it's the same formula, okay, but we interpret it differently. So it's stat, tables, chi-square test for association. We have the summarized data. My columns are the usually and rarely eating 3 meals. The rows are my gender. And I click OK. Again, we're looking for test, chi-square test. And we are still going to read the Pearson. Well, Okay, so step 3 here that I forgot to write a while ago, but hopefully you know it by now. Step 3 is to calculate the test statistic, which is chi-square and its p-value. So my chi-square from Minitab is 2.314. My p-value is 0.128. As always, then we got to make a decision. We make a decision by comparing the p-value to the level of significance. P-value for Minitab is 0.128. My level of significance is 0.05 or 5%. We compare digit for digit. 1 compared to 0. 1 is greater than 0, so P is greater than alpha, which means we fail to reject the null. In this context, if we fail to reject the null, that means the null is true and the alternative is false. So the distribution is the same for males and females based on the evidence that we have. Step 5, we write the conclusion. At the 0.05 level of significance, the distribution of 3 meals per day is the same for males and females. Questions? All right, we got one more to go. So scenario 10, and remember scenario 10, well, you may not recognize it yet, but it's going to be a little bit different. Scenario 10 deals with 2 variables. It says the data below gives the gold medal times for every other Summer Olympics for women's 100-meter freestyle. Can you predict the gold medal times by the year? So in this particular case, we have what is called bivariate data. We have 2 different variables. And if you go back and look about which distribution or which test to use, the only one where we had 2 pieces of data that were paired together was linear regression or correlation. So we've got to ask ourselves, is there a relationship between the year and the time? Okay, and then if there is, can we create a model of that relationship and make predictions? So this one's a little bit different. It's not just a pure hypothesis test. So we begin in this problem. The first thing we have to do is to identify which of the variables is going to play the role of the independent variable, which is your X, and which is your dependent variable, which is the y. Now, you may or may not remember, but if you go back and look at your notes, I kind of gave you some guidelines about how to make this decision. The standard rule of thumb is that the independent is in the left-hand column or the top row. And the time in this case would be your dependent because it is on the left or the bottom row. And if I think about it and use my little saying, we're saying that time depends on the year. Well, that reasonably makes sense. And so time is Y, year is X. And if you'll notice, that's how it's set up. You have X on the left and Y on the right. So my independent is the year. My dependent is the time in seconds. And it's important to know which variable is which from the beginning. We then took a look at the scatter plot, which gives us a way to visually analyze this relationship. We use our eyes to evaluate the relationship through the scatter plot. I need Minitab to create the scatter plot for me. So the first thing I need to do is go out and enter the data. Oh, come on. Okay, so I'm getting a blank worksheet. And so I would put year, which is my X, in column 1, and the corresponding paired value, which is time, in seconds, which is the Y. Again, I like to label from the beginning whether they're X and Y, and then I have to enter the data. And so I have all my data entered. Then we want to create a scatter plot. So it's graph, scatter plot, keep it simple. The Y is time, the X is the year. And then I tell it okay. And I get this scatter plot. Whoops. Well, guys, I can't get it to let me put this thing in there. Just get a new piece of paper. Okay, so we put our scatter plot in there. You want to then ask yourself 3 questions about the scatter plot. Okay, the 3 questions that we ask ourselves looking at the scatter plot is there an overall pattern? which there does appear to be some sort of pattern within the dots, does that pattern appear to be linear? And I think so. I think I could draw a line in there. And then the third question is, does it appear to be positive, negative, or zero? And I notice it appears to go down as the year goes up, the time goes down, which lets me know that this relationship appears to be negative. But so visually, we're saying, oh, yeah, we think that there is this relationship. Okay. But remember, guys, we do not get to rely just on our eyeballs. So then we go out and we calculate the R, which is the linear correlation coefficient. This gives us a measurement, a numeric value. This is more of the algebra analyzing or analysis. Okay, because I'm going to use the numbers inside a formula and get a value. So Minitab's going to do that for me. You've already entered the data into Minitab. Okay, we don't have to enter it again. We go to Stat, Basic Statistics, Correlation. Stat, Basic Statistics, Correlation. We're relating the year to the time. I click OK. And we get a scatter plot again, but, and I'm going to copy it over here on my paper again, hopefully. Okay, the reason I copied that is because I want you to realize that your R is here underneath the scatter plot on that output. So my R value is negative 0.904. So R is negative 0.904. Now, as a quick little reminder, remember that the R has to be between -1 and +1. And if you're looking at that kind of as a scale, the closer you are to 1, the stronger the relationship. So if you're close to 1, it's strong. If you're close to 0, it's weak. If you're kind of middle of the road, it's what we call moderate. So my gut, just looking at this number purely from a gut perspective, I would say that we have a strong negative linear correlation. I'm saying strong because 0.9 is close to 1. It is a negative value. Plus, we saw that it looked to be negative on the visual. And R only measures linear relationships, so it has to be a linear relationship. Okay, but again, we don't get to rely on our gut to say, yeah, that's what we think. Okay, we have to move on to step 5, which is to verify. And we're going to verify by doing a hypothesis test. Okay. on R. And the question is R statistically significant? And is there a linear correlation between the two variables? That's the two questions that we're ultimately going to verify, prove beyond a shadow of a doubt when we conduct this hypothesis test. So we begin, as we do with any hypothesis test, and we state the hypotheses. Now, for correlation, the hypotheses are stated the same way every time, all the time. Rho would equal 0, and rho would not equal 0. And that's really what you would write, or what you would choose if you're looking at the multiple choice questions on your test. However, you do need to understand what that means. If rho is near 0, that means there's no linear correlation, and R is not statistically significant. If rho does not equal 0, that means there is a linear correlation, and R is statistically significant. Now, again, you really only have to write or express what is in orange, okay? But you need to know or understand how to interpret that. So then, moving on to the second step of the hypothesis test, again, we modify it slightly. We have to calculate the p-value only. Now, I could use the test statistic, but I don't need it. So we need to go out to Minitab to get those values. We've already entered the data. It is stat, regression, regression, fit regression model. The response is always and forever the Y. The response is always and forever the Y. The continuous predictor is the X. Then I click OK. And remember, we get lots and lots of information. So we have to scroll down until we find the header, analysis of variance. Okay, we get lots of results, and we scroll down till we get to the header, analysis of variance. And on that table, we find the p-value. So my p-value is 0.013. Then the third step in this modified hypothesis test is to make our decision. And we use the same process that we've used forever to compare the p-value to the level of significance. The level of significance is usually given in the question, and most times for correlation we use 0.05. So if I make that comparison of the p-value to that level of significance, I have 0. Change colors. I thought I did, but I didn't. 0 compared to 0, 1 compared to 5. 1 is less than 5, so P is less than or equal to the level of significance. When P is less than or equal to the level of significance, we reject the null. In this context, if I reject the null, which means the null is false and the alternative is true. If the alternative is true, that means yes, R is statistically significant, and yes, there is a linear correlation. So based on my decision, I can now say R is statistically significant and there is a linear correlation between the year and the time in seconds that it takes them to do whatever the event was. Okay, so at that point, I now know beyond a shadow of a doubt that I have a linear relationship. So once I have proven that I have a linear relationship, the next step, which I think I'm on number 6, is to create the model or the equation that fits that relationship. It's often called line of best fit. And again, we actually already have that in Minitab because we did stat, regression, regression, fit regression model. And once you do that and get your results under the header regression equation, but then you need to translate it. You need to get rid of these words. Okay, you have to get rid of the words. So I have Y okay, Y equals 349.0 minus 0.1476x. Okay, you take the words out, but leave the variables in. Okay, Naomi, I know it's 12:14. Hold on just 1 second, okay? I'm finishing up class. Can I call you back? Okay, hold on just a second. Naomi, hold on just 1 second, please.
Okay.
Naomi? Naomi, are you still there?
Yes, I'm still here.
I'm sorry. I know it's after 12:15. I'm almost finished with this problem. Can you hang on and let me finish? So you'll
Okay.
have the benefit of it, and then I'll post the recording. I do apologize for interruption, but apparently they've had to take my mother to the hospital. So I'm gonna finish this up. So we got the model. Again, the biggest thing about the model is take the words out. Once you get the model, then they may ask you to make a prediction. And so if I look at the quiz, it'll probably ask me the next question after it asks me to find that model near the bottom of the test. It's going to ask me to make a prediction, and it's going to give you a value. So let's see. On question 71, it asks you to identify the equation. And then on question 72, it says to make a prediction about what the time would be in the year 1996. So when you get to question, it's 72 on the test, but it would be like step 7 in this process. You're going to be asked to make a prediction. Okay, and they're going to give you that the year, which is your X, equals 1996. That was given in the problem. So you'll be given that value. Okay. Don't overthink it. It's a plug and chug. Okay. It is a plug and chug. So I'm going to plug in. I would have Y equals 349.0 minus 0.1476 times 1996. Okay, so I have 349 minus 0.1476 times 1996, which is 54.3904. So in 1996, the time would have been approximately 54.39 seconds based on our model. And that may not have been what it actually was, but again, that's based off of our model. Then the last two questions are related to the coefficient of determination. And the idea behind the coefficient of determination is, should we even be using the year to predict the time? So R squared, that's kind of the next step, is you want to determine R squared, which is the coefficient of determination. And it's again kind of the question of, should we use the year, which is X, as a predictor for the time, which is Y? Is it even appropriate to look at that relationship? We determined there was a relationship, but is it a good, strong relationship? So again, we get R squared from Minitab under the header model summary. Okay, now again, be careful, make sure you read the right one. The model summary, R squared, that we want is just plain old everyday R squared. So R squared for this problem is 81.79%. The rule of thumb that we use is if R squared is greater than 50%, then we're going to say, yes, we can use it as a predictor. So 81.79% is greater than 50%. So we can say, yes, that year should be used as a predictor for the time. And then the very last step is you have to formally interpret the R. Okay, so the last step is to formally interpret R squared. Okay, so R squared, we would write approximately 81.79% of the variation in the time can be determined by the variation in the year. Now, real quickly, and then I'll be done. I'm sorry to have kept you over. This statement is pretty much the same every time. You have to change the R square value. The variable that comes first is always the Y, and the variable that comes second is the X. And the other important piece is you have to include the word variation. So that finishes the review sheet. Again, I apologize for keeping you over, Naomi, but do you have any last minute questions?
No, I don't have any questions. Oh, I have one. Is the final review thing, would I be able to like do half of it one day and then half of it like the next day? Like would I be able to go back to it? Or do I have to do it?
I think you can go back to it as long as you save it.
Okay. That's
Okay. All right. Thank you, Naomi.
You're welcome.